Hey, my name is Mohamed Arafa. I am a senior principal engineer with the Data Center Engineering and Architecture Group. I'm going to be talking to you about the Intel Optane DC persistent memory architecture, and then Lily Louie will be presenting kind of the performance aspects of this new technology. So this is a pretty exciting opportunity. It's something that we have been working on for many, many years. A large team of folks have been working on it. It's really something that happened once in a career lifetime for me. If you think about DRAM, it happened about 40-some years ago. Then NAND was 20 years ago. So it's about time to have a new change in memory technology, and we think that this is what's going to kind of be providing it. I'm not going to be spending quite a bit of time on talking about the problem statement. I'll just be pretty brief in there. A lot of people have already seen that many times. We're going to move to the modes and the population of this module. Then we're going to go under the hood and dig deeper into multiple aspects of this technology, whether it's the protocol that we use, the optimization that we have done on the module, the optimization that we have done on the system, security and RAS and endurance features, because these are the questions that usually people tend to ask questions about. The problem statement is relates to the fact that unprocessed data is really, to some extent, useless data. And you have seen, you heard Naveen this morning talk about the amount of data that has been generated over the last 5 years, and the fact that only 2% of this data is only being processed. That's kind of a shame, so that's why we're trying to address with this technology here. So if you look at any data set that you would be having, so usually you can divide it into two different sections. Usually it's different shades of gray, but you will have hotter portion of the data, a portion that gets accessed more frequently, and cooler portions of the data, portions that do not get accessed that frequently. And what people usually do is that they put the cooler part of the data into the storage stack, the hotter part of the data into the DRAM, and then that you do that in order to optimize performance and cost. Of course, you want to put everything in DRAM, but it gets too expensive and it's not persistent. And if you put everything in storage and you have a skimpy DRAM, then the performance will suffer, the system will be cheaper. If you look at the details of that, when we looked at it 10 years ago, it's not just the DRAM too, because there is a CPU caches which have very low latency in the pico-nanosecond range. The DRAM has around 100 nanosecond latency usually. And then you go to the storage stack, and then you get into the hundreds of microseconds and milliseconds for the network attached stuff. So what we have noticed right away is that there is a big gap between the storage stack and the memory stack, and we thought that we can fill this gap with two new products. One of them launched about a year ago, which is the Optane SSD. And today we just launched the Optane DC persistent memory module, which puts that even closer to the DRAM. And we are just doing that to be able to move the data closer to the compute and also maintain persistency, because as the data sets gets larger and larger, you really want to be able to shut down the power without losing your data and having to rebuild all this massive data again. So the Optane DC persistent memory, and actually we have some modules in the back, so we can kind of pass them around if you want. Lily, can you help? So it has the genetics of both the memory and storage. From the memory side, it has performance very comparable to DRAM, meaning low latency. And from the storage point of view, it has a persistency, it has a larger capacity that you don't see in DRAM today. So it has the genes of both the memory and the storage. And this is a theme that you're going to see throughout as we kind of talk along. Now let's talk about the modes and population. So this was architected from day one for flexibility in use. As Ian kind of mentioned a minute ago, we really were envisioning some usages, but people wind up even using that for other things that we didn't even dream of. So for that, we try to kind of maintain as much flexibility as possible while not making the product as complex as possible. So we thought mainly about two modes, and Ian kind of touched on that quickly. I'll go a little bit deeper into that. And then Lily will talk about the specific flows of these modes later in this presentation. So memory mode was meant to mimic volatile memory DRAM, except that you get very large capacity. And the way we do that is by front-ending the Optane DC persistent memory with DRAM DIMMs, which is huge cache that have never been used before. And think about the cache that people are accustomed to.
So Mohamed, is that in that configuration, it's like you could have a DRAM DIMM and an Optane DIMM, and you could configure it with memory mode or app direct? It doesn't actually have a particular DIMM that has DRAM and Optane on it.
So we don't have today a module that have both DRAM and Optane on them. We're going to show in the next slide how they are populated on an actual system. But it's really, think about a Cascade Lake system to be having 12 available slots per socket, per CPU. 6 of these can be DRAM. The other 6 can be Optane DC persistent memory. The caching, though, that happens between the DRAM and the Optane DC persistent memory here happens on a memory controller granularity. You don't have to have all the channels in a memory controller having Optane persistent memory. The caching just happens within each memory controller. So you really look at your memory space, you will have what we call near memory, which is DRAM, and far memory, which is the Optane DCPMM. The near memory doesn't show up in your system memory space because it's just being used as cache. And it's a humongous cache. It's like tens of gigabytes of cache that you are having in your system using the smallest DRAM capacity DIMMs. So we did that because we want people to start to use this right out of the box. So there is no software and application changes. You just run the software the same way you were running it into a DRAM system. And the hardware takes care of the caching and ensuring kind of that the performance is as similar to the DRAM as possible. So when you hit data that are already in the DRAM, you get the same performance as DRAM. Only when you miss data in the DRAM that you see the additional latency that you get from Optane DCPMM, and Lily will be talking more details about that later in this presentation.
So is having the mix of traditional DRAM and the HDRAM required for that? Because doing the math, you're only using 9 modules to max out the 4.5 terabytes of the Intel HD optimized, right? So
we have a slide on that coming.
Okay.
So we're going to talk about kind of what you can do from population. Of course, your matrix as far combining DRAM and Optane DCPMM can go up the roof as far as kind of validating it. So we try to limit it to some configuration while offering flexibility to what most of the customers would be using.
You're not going to put all 12 slots with the HD.
That's not so. So you need to have DRAM. You need to have at least one DRAM DIMM, right? But from a validation perspective, that's not a practical use. Nobody will buy a CPU socket and just put one DRAM DIMM in there, right?
Right.
So from a validation point of view, we limit it to just configuration that we thought are more prevailing. But technically, you can have one DRAM DIMM and one Optane DIMM, and it will work in this mode.
So Mohamed, I'm not that well versed in memory controller technology, but is that on the CPU?
Correct.
Okay, so the new Xeon scalable CPUs have the memory controller that supports this.
Correct. So that's launching with this. The Cascade Lake CPU, the new Xeon scalable process SP CPUs, would have a memory controller that support the caching for this mode and have the hardware for it.
What is the RAM Optane ratio in one DIMM?
There are challenges with that. That's maybe something that we can consider later, but as it is today, we didn't go this way. Part of the reason is that if you kind of put a specific DRAM and the specific Optane capacity on the same DIMM or memory module, then you tie your customers into a specific ratio of the two. And our customers have told us that they want flexibility. They want to be able, depending on their workload, to change the cache to for memory ratio to the best they can. They want to be able to purchase the DRAM from the supplier that give them the best cost and stuff like that. So it wasn't desirable kind of it's technically feasible, but has some technical challenges with it, of course, right? But it's not something that we chose to do on the first generation.
Okay.
Okay? And the data on the module is will still be encrypted. We're going to talk about the security aspects of that in a little bit. And I think that kind of cuts through everything here. So the other mode that we have was app direct mode, as Ian kind of highlighted quickly. But for this mode to be used, you need your software to be modified for two reasons. The software need to know which portion of the data to put in the volatile memory, the DRAM, and which portion of the data to put in the Optane DCPMM. So there is a data partitioning part of it, but that's not it. If they want to be using the memory as persistent memory, there is changes to the software on the application itself that need to happen. So a work started by a colleague of ours named Andy Rudolph in SNIA to come up with a consistent persistent memory programming model across everybody. So all companies kind of agreed to adopt this model, and it's actually the standard as it is right now. So this model, the way it works is that you set up the persistent memory using like the file system. Then you map it into memory space. It's called DAX mode for direct access mode. And then you can just do cache line load stores to it, the same way you treat it with memory. Now, of course, from a programming model point of view, the software have to take ownership of making sure that the data that they want to be persistent have reached at least the memory controller on the CPU. So let's kind of talk about it a little bit. In this specific case, you still have DRAM and you still have Optane DCPMM, but both the capacities of these modules and DIMMs are visible in memory space. So they add, from a capacity point of view, they will add to each other. And what happened is that the software will need to take care of flushing the data from all the CPU caches and make it reach the memory controller. Once the data reaches the memory controller, we guarantee that the data will be reaching persistency even if the power is lost. Pretty much there is enough energy stored in the system so that if you suddenly lose power, the write pending queue in the memory controller gets flushed automatically, as well as all the queues on the DCPMM module will also be flushed to just guarantee that the data have reached the media.
There is a capacitor or something in the DIMM?
Yes, and we're going to talk about that in a second. Okay, so this persistent memory is cache coherent, can be used with DMA and RDMA, and has a critical feature that NAND does not have, which what we call in-place persistency. So NAND has a concept of blocks, right? So you cannot really erase a page. You have to erase a big block. This media doesn't have that at all. You can just pretty much erase a very small granularity cache line size like data and just write it in place. So this garbage collection aspects, write amplification, these concepts don't exist, which gives us the consistent performance which we need because this is behaving as memory. It's not storage anymore.
Cache coherency.
Yep.
Becomes a tricky issue. I have to go in my mind to things like if a server gets downed and it happens to be a server within a high transaction database, whether it's deliberate or not, a crash can happen. What really does cache coherency mean in terms of transactions that take place during the reboot process? Now, I understand that the memory is persistent.
Correct.
So it's going to have in its buffer, whatever you want to call it, whatever transaction hit that CPU before the crash took place. Mm-hmm. What do we do about that gap in between? And I understand we're starting up a lot faster now.
Yes.
It's some magnitude of X percent, 4 minutes to 50 minutes, these kinds of things. But how does that equate to cache coherency?
Yeah, so the cache coherency means that the CPU or the application doesn't have to worry about getting the data in and out of the CPU caches. and the caches are managed really by the hardware. So if a data gets modified, you're not going to be getting stale data. So this concept here for this applies exactly the same way as DRAM. So there is no difference. The only difference is that, as highlighted in here, the software need to use one of two instructions, which is CL flush opt or CLWB, to just ensure that any writes that they have made that they want to be persistent gets flushed out of the CPU caches. Because if it stays in the CPU caches and you lose power and it's dirty data, it's gone.
So something like that would be done at a power fail interrupt, or you think this is going to be done anytime an update is made to the data?
So the libraries that developed based on the SNIA programming model already have in their libraries the flush operation in to ensure persistency. So that's why they need to modify the software to just make sure that these flush operations happen.
So from a practical perspective, if I have an SAP HANA database, and I want to take advantage of terabytes of RAM with a mix of the two different types, I can just use this flag to say that nearline data should go to persistent storage. In-memory data that I'm going to run a lot of analytics off goes to traditional DRAM, and then the system itself just so in SAP, it should be a really simple change.
Correct. So what SAP did is that they architected the way they place their data and their software from the ground up for this technology. I think Lily have one slide on that coming, so she's going to talk to you a little bit more details about what SAP is doing. But they really kind of they know which data is in DRAM, they know which data is in persistent memory, and the data that's in flight, they use these operations, CL flush opt or CLWB. They have a delta merge operation where they kind of flush the data that they have updated in the delta region in DRAM into the Optane kind of memory. So they kind of use either our libraries or a modified version of the library. So what we have with these libraries is that they are actually open sourced. They are available for everybody. A lot of people just use them as is. Other people just take them as just a starting point, and they start modifying from there.
When you say cache coherent, is the cache coherent across dies, cores?
Sockets.
Sockets.
Yeah,
so a multi-socket system with 12 cores or whatever.
The data can be in the cache for the other CPU, and the hardware will take care of the coherency for you. It will take care to tag this cache line if somebody else have modified it, and so that you don't use stale data. It's just the same mechanism that we use really for DRAM.
For memory, yeah.
Okay.
You mentioned DMA and RDMA capable. DMA makes sense. I'm trying to understand where RDMA plays out here.
This is kind of for replication kind of across sockets. And I think also Lily have an example. I don't know that you removed from the slides, but I think there was, no? It's not there? But okay, so let's talk about it. So this is if you want to replicate persistent data across socket, you can just use RDMA to get the data from one module on one socket to one module on another socket. If you need to do that for storage prior, no, not in a socket, but I mean in another node across the network. So you have like two socket system here, two socket system there. You want to replicate this data so that if this node dies, you have a copy of it there. You can RDMA some of the data to the other remote node.
NVMe over fabric kinds of?
Exactly, yeah. So you just use the same mechanism that you have.
Memory to memory.
Except that you're doing it memory to memory. You don't have to go from storage to memory, from memory to memory, then memory to storage, which saves quite a bit of time.
So I'm a SAP guy, so I'm going to ask the SAP type question. So if I'm doing a scale out SAP system in which I need to do replication from one system to another, is SAP leveraging that to do replication from two in-memory systems for resiliency?
Yeah, I'm not familiar with how SAP specifically does the replication, but they can, yes.
Okay.
So, and from the security perspective, if I steal one of these DIMMs from a server,
we have one slide on security, and we'll talk about this specific point in a second. Okay. Now, before kind of I move forward, we just talked about AppDirect, we talked about memory mode, and yes, we support both of them together. So you can go on and partition partition your Optane data center persistent memory into two regions. Treat one region to be cached in DRAM and being treated as volatile, and another region to be not cached in DRAM and being treated as persistent. And we call it mixed mode, which is a combination of app direct and memory mode. And that's kind of what we meant by additional flexibility that we kind of have added. This is not a mode, but you can think about if you have an app direct mode that's byte accessible, you can write a driver on top of it and just use it the same way you would use a storage device, right? So we call that storage over app direct, and it's exactly the same usage as app direct, except with a driver that just handles the atomicity and the block transfer, whether it's 4K byte or something else, to the Optane media.
Quick question.
Yes.
And this has probably been talked about before, but at this point, what does higher endurance mean in a quantifiable way?
We have a slide on endurance. We'll talk about that in a second. So I knew we get these questions many times, so we have already slides for them. So from a population kind of rule point of view, this is an animation. It's meant to show that it's flexibility. You usually have 6 DRAM DIMMs because you want to get the maximum bandwidth out of your near memory, or even if you are in 1LM plus app direct, and then you can place up to 6 Optane DC PMM modules per socket. They can share the same channel with the DRAM. At boot, BIOS will detect their presence and will know that they are there, and will kind of, depending on how you configure them at boot, they will be either use them as in memory mode or in app direct mode, or a combination of the two. And with that, we'll go kind of under the hood for both the module and the system, and try to kind of highlight where the multiple innovative approaches that we took in order to integrate things together for performance. So the first hurdle that we had, we just said that the BIOS will detect the presence of these modules, and there is a need then for the host, the CPU, to communicate with them. And for that, we came up with a protocol that we internally call DDRT, for a transactional DDR. This protocol runs on the same DDR4 bus, same physical as DDR4, and can share actually DDR4 traffic on the same bus, and it communicates with the host, the CPU, via what we call a request grant scheme. So if the CPU needs some data from the Optane DCPMM, it will tell it, can you get me this data? The Optane DCPMM will go retrieve it, and then when it's about to be ready, it will send the request command to the host, telling it that, hey, I have your data almost ready. When can I get the bus? The host, being the master of the bus, and decide on the time to give the bus back to the Optane DCPMM. And at this point, it will send a grant signal to the Optane module, which will then kind of put the data on the bus and gets consumed by the CPU. So this is how they handshake. Of course, we didn't have additional signals on DDR4 to be able to have this thing. So what we did is that we looked at some of the signal that comes to the Optane DCPMM that we were not using. So there were 2 pairs of clocks, additional ODT signals, et cetera, and we repurposed them for this purpose. So when you put the Optane DCPMM in the system, BIOS will detect that it's a case. We'll program both sides to use this signal in a different manner, and this signal is being point-to-point from the CPU to the Optane DCPMM. The other DDR4 DIMM that's sitting on the bus doesn't see them, and then we kind of handle the communication protocol this way. The transactions can be reordered. So unlike DRAM, the host CPU does not micromanage Optane DCPMM. It just tells it, I need this data, and whenever it's ready, it gets back. It can come back in order or out of order. It just doesn't matter. And it's a 64-byte accessible the same way DDR4 is. So as we described before, the Optane DCPMM has the same genes as memory and storage. So in memory subsystem, in the memory controller, everything is implemented in hardware because latency is at a premium. There is not that much media management other than just tracking which pages are open and stuff like that. So we implement everything in hardware. For the SSDs, everything is implemented in the firmware on the SSD. There is actually DRAM on the SSD. You move the data in the DRAM, and then you send it back later, and you handle garbage collection and all this kind of thing. For this, we couldn't tolerate the latency of getting everything go through a firmware. And we also wanted to do some media management. So we wind up implementing a hardware pipeline for the data and command paths, completely implemented in hardware. But this hardware is programmable using a firmware. So the firmware kind of plays with the hardware, control it in different configuration, but once it's configured, everything kind of goes in hardware. If the firmware needs to do some media management, it takes advantage of some of the hardware to kind of do this management on the fly, completely transparent to the host CPU.
The first time I've heard media management and Optane being mentioned together here. Are you doing some sort of, I'll call it logical address translation to move data that, may have overacted on a particular byte or bit or whatever?
Exactly. So if you look at, if you remove the full DIMM heat spreader that's on the module, and you look at what's the components that are in there after removing the thermal paste, right?
Don't do it, Rob.
There's thermal paste all over the place there. So you would see that there is a component here that we're calling AIT DRAM. And AIT stands for Address Indirection Table. So there is actually an indirection table that we use to kind of pull where the system addresses translate into physical addresses on the media, because we do some wear leveling for the media in the background while transactions are happening. So that kind of answers your question. So yes, we do address translation, and the table is completely saved in the DRAM. That's a single DRAM chip that's on this module. Okay? Now, on the module itself, there are...
the address translation table is in DRAM?
Not address translation, address indirection table.
Okay. The address indirection table is in DRAM?
Correct.
Which is not persistent.
Which is not persistent.
And you can rebuild it.
So
it means the power goes away, your address indirection table goes away.
No, I have a copy in the persistent memory. So whenever you update anything for the address indirection, it gets updated in the persistent memory so that if I lose the DRAM, I don't care.
Okay.
We are just using the DRAM here because it's a faster access for this large table.
So the one that's actually in use is the one that's in DRAM. However, there is a copy that's backed up.
Absolutely. Okay? So if you look at this module, you will find that it's actually a system on a DIMM form factor. There's a lot of components that are in there. So beside the 11 Optane devices, you have a power management IC that generates all the rails for the Optane media as well as the controller, because we have to live with the rails that come to the DIMM, which is only 12 volt and 1.2. So everything else that we have to generate on our own. DDR5 actually is going this path. It's going to be coming like in 2 to 3 years. You have an SPI flash where the firmware for the microcontroller that's on the DIMM kind of is being run from. You have DQ buffers for signal integrity reasons. We talked about the AIT DRAM, and you have energy store capacitors on the module that just guarantees that if we lose power at any point, we'll have enough energy stored to flush our queues back to the media. And the heart or the brain for this module is a controller that's highlighted in here. It's a pretty elaborate and complex controller that have ECC engine, encryption engines, buffers, power and thermal management. We do manage the power and thermal characteristics of this module. You can literally add BIOS program how much power you want this module to operate at, and it will operate within this envelope. The other thing I want to highlight, because Lily will touch on that in a second, is that the transfers to the media happen on a 256-byte granularity. The transfers on the DDR-T bus is on a 64-byte granularity. So we really retrieve 4 cache lines, and we return a cache line there. That has been done for ECC efficiency. So when you see some of the number that Lily will be showing in a second, you will understand kind of why that's the case.
Yeah. Excuse me, are there any cooling considerations that you have to worry about?
That's why there is a full DIMM heat spreader there. Yes.
Yeah.
Yes.
Right. And that's all that you need. There's nothing
So
extra you
the
need to do in
cooling
terms
is
of
function
airflow
of
inside?
what the system is designed for. Some customers have told us that they can cool their system up to 18 watts. Some other customers have told us that they can go to 15 watt. Some customers have told us that not even for cooling, for power delivery, they can only do 14 watts. So that's why we're allowing them to program the power limit for the module to the whatever they want to have. Okay?
And all the Optane devices are accessed in parallel?
Correct. All of them are accessed in parallel, minus the spare. Okay? So I am behind. Sorry, Lily. I'll try to finish in 3 minutes. This is not just the module. It requires enablement all across. There were changes, of course, in the software, the enablement that we talked about. BIOS had to kind of accommodate all that. CPU has to change, for example, for memory mode, to do the caching and stuff like that. So it's really a full system view, and that's why we think that only a company with the scale of Intel can really tackle this thing, because there is no other company that have the view of the whole system view the same way we do in here. Okay, so I'll touch on 2 points. One of them is security, and the other one is endurance, and that's gonna be it for me today. So on security, there are 2 encryption keys. They are 256-bit strong AES XTS encryption engine on the DIMM that generate these keys. One of them is used for the volatile region when we are in memory mode. The other one is used for the persistent region. And the reason that we have an encryption key for the volatile is that whether we want it or not, this media is persistent. So our protection model is protecting data at rest. We don't want somebody to pull in a module from a system and just go and put in another system and be able to retrieve your bank account or social security number and just put in there. So the volatile key will get just thrown away every time power gets recycled or we hit resets, the same way DRAM would. So we're effectively doing a security race for security, protecting data at rest. Yes.
I'm a little confused. I understand it generates a new 256-bit key each time it boots for that particular cache of memory. Who has access to these keys? How is it accessed? If it's freshly generated, does it get pushed elsewhere and somehow somebody might have access to it?
The keys never leave the module. So
Okay.
each module have its own keys that are generated using a random number generator engine on it.
Okay.
And never leaves the module.
So
Now-
it's really for the computer's access to the data.
Correct. Correct. So once you boot, the engine will go generate a key, right? And then this key will be used, say, for the volatile reason. If you lose power or you reset, I throw away this key, so the data on the module is just garbage. Nobody would be able to read.
I got that.
Right?
and the-
For the persistent case, sorry, just let me complete it. For the persistent case, you have to have a kind of a passphrase to unlock the module. The passphrase is the same way that you do for your SSD. So you supply a passphrase, it's used to unwrap a key, and then the key is then, this unwrapped key
Is
is
that
used to
manually generated or is that also auto-generated?
It's hardware generated on, the key is hardware generated on the module. The passphrase, you get to pick whatever you like,
Okay.
of course, right?
All right, fair enough.
But it's different for each module. That's kind of the point.
Oh,
So-
It can be different for
that
each
is
module.
So
confusing.
in RDMA, is that what we're using to do system-to-system RDMA replication, or what is that mechanism for initiating RDMA from one node to another?
Just through software, if you have to have an RDMA software. In order
Okay,
to be
so
able to do that.
it's the software, you're not providing a mechanism for the replication, you're just
No.
providing the data path.
The ability to do that.
Okay, yeah.
Now, for people that want to get dispose of the DIMM, they want to get a more secure way to erase the DIMM other than just throwing away the key. And for that, they have the capability to do a full overwrite of the data of this module with zeros.
How many times does it overwrite?
Once. You don't need to do more. There is no residual electromagnetics in there to require more than once.
So there's a mechanism for an eager zero.
Yep, just write everything with zero, and then the DIM will be completely fresh. And then we do firmware also authentication because there is a firmware on this module.
Could there be like, I don't know, like a spike or something like that that could cause the data to refresh and all of a sudden everybody that's in the middle of what they're doing has to start over?
No, so all the media management operations are done in the background and maintaining data integrity at all times. So it's being managed by the hardware that we have on the module. If something fails, yeah, you can get data loss.
Yeah,
Like say
yeah.
the controller failed, and there is nothing that you can do about that.
So we're going to talk about RAS later. So if I have to replace a DIM, what happens when I have to replace a DIM?
If the DIM is being used in an interleave set, of course you lose your whole interleave set. If the DIM is alone and you just have to replace it, you just have to bring a new DIM, put it in there, and then just create namespaces and just choose a new one. If it is in app direct mode. If it's in memory mode, you just get, it's volatile, so you just put the new module in there and it should work. I won't touch on RAS quickly, but we designed this with server class RAS kind of in mind. We have single device data correction and double device data corrections. Two devices literally can fail on this module, and it will continue to work. And then we're supporting a whole bunch of other enterprise class data. So from an endurance point of view, it's kind of the last slide. Apologies, Lily. So we decided to use the petabytes written as a metric for the endurance of this module. And it's a petabytes written. The example that we're giving here is for a 256 gig DIM at 15 watt using 4 kind of successive cache lines. You can see that you can get between 200 and 370 petabytes written. And that should be enough for this specific case, to last you for the life of the module, which is, we guarantee we have a warranty for 5 years, right? So if you go look at the bandwidth, right bandwidth that this module can have, times 5 years, that would be pretty much the number of petabytes written that you have in here. Assuming you kind of use it 24/7, 7 days a week, continuously for 5 years. Now, and you can kind of also tell how far are you from the end of the endurance lifetime of the module by looking through the smart register, the same way you do really with SSDs today. That's all I have, and I took more time, apologies. But there were good questions. Any final question before I hand to Larry?
Yeah, I'm sorry. Just one quick one. And I'm sorry if I missed this earlier. With hard drives, we're used to like RAID. Mm-hmm. So is there something similar with the Optane?
No, we don't support hardware RAID or mirroring on this technology at this point. So there are some complications for the persistent nature of it, and there is issues with the cost too. And a lot of customers have told us that for this to be meaningful, you have to replicate across node. So RDMA plays a better role than if you do RAID. Because if you RAID on one system and then you lose a system, you're dead anyhow. So.
Okay.
But there's got to be one that becomes the main controller or main master, right? If you're getting in a multi-DIM situation.
Yes, once you RDMA, then you can decide which one is your master, and if you lose a node completely, you can just retrieve from the other node.
Okay.
So at the end, sounds like that you're practically not forced, but actually to keep the system balanced. I mean, now you have more than 100 cores in a single system. So to keep the ratio between RAM and CPU feasible for many workloads, you will need some of this anyway.
Yep.
So
Yeah,
it's
but-
not kind of an option, you know.
You mean mirroring and RAID, or some?
No, so you need some of these DIMMs to get the, you know, enough amount of RAM, or even if it's not
of course.
RAM.
Yeah.
Yeah, capacity of RAM at the end to
So
you know,
she's
to
gonna
fill.
she's gonna be touching on that. So I'll just direct this question to her.
Did you say it's double device correct? I mean,
Yes.
so you could lose two of the 11 Optane media chips and it'd still run?
No, it's two with the spare.
Two
So
with
there
the
is one. If you lose one, you continue to run. Then we kick in the spare. It's like a spare tire.
Yeah.
And then you can continue to run. And the spare can die, and then it will continue to run.
But you better replace it soon.
Yeah.
Of course.
It's like the low
Because
gas
after you lose
warning.
two, you don't, you know, if you lose anything else, you lose gas, right? So yeah, absolutely.
That's the operations problem at that point.
Well, what we do
Or
is that
UPS.
once we initiate a spare, even the first one, it shows up in the smart register, and there is interrupts that goes to the system. So they know once they got a spare that, hey, something wrong.
So something's wrong.
And this is really meant to just keep the system running, so they don't have to schedule a service right away. They can wait for a little bit and just schedule it.
Unless there's something systemic that's causing the
Correct.
memory to fail.
Absolutely.
That becomes a bigger issue.
Yep.